Okay. So a very good morning once again. So quickly run through from where we stopped last time. Okay. So in our last class, we talked about computer architecture and organization from the design perspective. Okay. Computer organization and architecture. Okay, so we were able to deal with two major aspects. We said, well, the architecture deals with the instruction set, the memory addressing techniques, the bit representation of data, input-output mechanisms. And then we said the computer organization deals with the control signals, interface between the computer, memory, peripherals, the CPU, and all of that. Good. And we spent quite some time looking through the VHDL code. We pulled up the model sim for simulating VHDL programs. Then we said that the computer architecture is in two folds, okay? Here, we want to talk in terms of the instruction set architecture and also the hardware system architecture, okay? And then we made mention of a few things you already know, the von Neumann, the Harvard, the modified Harvard architecture. And then we also looked at architecture based on the number of processors they have, the single instruction stream, single data stream, single instruction stream, multiple data stream, the multiple instruction stream, single data stream, and then the multiple instruction stream, multiple data stream. Then we went on to talk about two types of, or two design models for instruction set architecture, the accumulator-based instruction set architecture and the general register based instruction set architecture. And then we're able to put up a schematic in that regard and then talked about a few things, okay? While the accumulator based have just one register, which is the accumulator, then the register based architecture have quite a number of registers, okay? Good. And then we'll just make mention of the machine level instruction at this point. Let's see.
Sorry, sir. Did you say that the
Well,
accumulator base
I can
has
tell.
only one register? I thought you said that it has only one register that can control.
Hello, I can't really hear you.
Because I remember from the diagram we had like three registers in there. The
Okay,
MBR,
yeah,
the
yeah,
MBR, and
yeah.
sir?
The accumulator based instruction set has one storage register that can be controlled by the user in the CPU. Okay, is that clear?
Okay, sir.
Yeah, and that particular register is the accumulator. That's why I said the register, single register control that can be controlled by the user is the accumulator. Yeah. Yeah, we have the memory buffer register, the memory address register. Those cannot be controlled by the user. Okay. Is that clear, please?
Yes, sir. Thank you.
Okay. And now, let's say machine level instruction. So well, we want to say machine representation of instruction. How do we represent instruction? Okay, when we now have to deal with this computing device. So at the machine level, operations must be translated to the binary sequence, right? So we want to deal with binary sequence. So each assembly instruction, which we know is the symbolic instruction, is derived from the machine instruction. So if we say, for instance, add X in the accumulator-based architecture, for instance, and we see that this can be broken down into the operation part and the operand part, okay? So we have this now broken into two parts, the operation and the operand, okay? Now, the operand is a quantity to which an operator is applied. Okay? So let's get that. The operand is defined as a quantity to which an operator is applied. So if we say m minus n, for instance, the operand of the subtraction operation here are m and n, okay? So the operand of the subtraction operator are m and n in this case. Then we have the opcode. So it is a mnemonic used to refer to the microprocessor instruction in the assembly language, okay? That's it. And now the logical instruction between two parts of the instruction is represented in binary as a machine instruction with two fields, okay? So we're going to see some examples right now, and those two fields are the opcode field and then the address field, okay? So the opcode field is a type of field that identifies the type of operation to be performed. And the address field gives the operand location, okay? So still on this, we will see that the opcode field and the address field are stored in the memory as a sequence of bits. So instruction is stored in in the memory in a memory word. Let's put it that way. So the memory word now is a number of bits, and that determines the data bus size also. So to determine the data bus size, the number of bits found in the machine instruction is determined by this simple formula. Let's write this. Word size is the same as the size of the opcode and address field. So in other words, we have something like this. We have opcode field here. And then we have address field here. So this is 4 bits, and we have 16 bits here. So we can present this in a more formal structure, say 0000, that's opcode. Then let's say we have 0000 0001 0000 0101. So this will be the address field. So this is for the accumulator based architecture, machine representation of instruction. So the opcode field size is the same as log m base 2, where m, where m is the number of instructions, is the number of instructions with the opcode and direct address field. So in the case of the general register-based architecture, we have a different form. Now, here we have 4 bits for the opcode and then 16 bits for the address code. But for the in the case of the general register-based architecture, we have 4 bits for the opcode field, another 4 bits for the register address, and then another 4 bits for the address field. So let's look at that quickly. So we have opcode field, and we have register address, and then we have address field. So this is 4 bits, then 16 bits. So we can have a form like this, say 0111, 0100, for instance. I have 0000, 0011, 1111, for instance, okay? So this is 4 bits here for the opcode field, another 4 bits for the register address, then 16 bits for the address field. And this is for the general register-based architecture. Machine representation of instruction. Okay. And the address, let's say for us to address n registers within the CPU. Now the address of the register field must not be less than log n base 2. Okay. So with this, let's quickly run through. Well, this is just to conclude the part we talked about last week on architecture. So let's quickly run through computer organization. Okay. Computer organization. Well, we have a simple frame where we have, say, the CPU, and then we have the memory, then we have the output devices, okay, and then we have the input devices. Okay. They will say this links up to this. And then this coming all the way. So let's say it just goes all the way. Apologies for the rough drawing, okay? Let's see. Let's wipe that. Then that. Then for this, we have this linking up. Now we have that this memory is connected to this. This is a control. There's a control bus. Okay. We have this way. And this is bidirectional. This is the data bus. This data bus. It goes all the way. This equaling the data bus. Then we have the address bus coming this way. This is the address bus. Yeah. Now, you recall that we said that the computer organization deals with the control signals, right? Control signals. And also the interface between the input output devices, the CPU and the memory. Okay, so this is what it is for the organization. And the computer system itself, we know that it consists of the CPU, which is the processor, the central processing unit, the memory unit, and the input output devices. And these are all connected via the system bus. So the system bus consists of the address bus, consists of the address bus or data bus and the control bus. Okay. And we know that the bus is more like a wire. So it's used to represent the group of electrical signals used for conveying, information within the system. So the bus itself is more like a signal wire. Okay, like a signal wire. So how about the address bus? The address bus. Now, it is a unidirectional group of lines or wires used by the CPU to send out the address of the memory location to be accessed. Okay? So if we have this, then let's see the address bus. Now, group of lines used by CPU to send out the address of the memory location to be accessed, right? So here, the width of the address bus determines the capacity of the memory addressing system. Okay. So if we consider the 8086 processor, for instance, 8086 processor, now it has two 20-bit address bus. Okay. So in other words, the physical memory of this processor can be addressed up to 2 to the power of 20 bytes or 1 MB. So for the Pentium, for instance, can address up to 2 to the power of 32 bytes, which is up to 4 gigabytes memory. Okay. So also the address bus is used by the CPU to select a particular input or output port. Then we have the data bus. In this case, it is bidirectional. Group of lines. That connecting the CPU, memory, and other peripheral devices. So the width of the data bus indicates the size of the data that can be transferred between the CPU memory and the I/O devices. So the width and the size data can be transferred between the CPU, memory, and input-output devices. So still on the 8086 processor, for instance, with 20-bit address bus and 16-bit data bus, and the address, or better still, this address is 2 to the power of 20 bytes, like we said, or 1 MB. Now, each data transfer involves 16 bits. okay? While for the Pentium, where we have 32 addresses and 64 data lines, they address up to, they can address up to 2 to the power of 32 bytes, which is 4 gigabytes of memory, and each can transfer, can do data transfer of about 64 bits. So it can move 64 bits each, you know, on and on. And now we have the Core I series and the likes. Then we have the control bus. So this carries synchronization signals, okay? Carries synchronizing, this is N. Signals. So here it sends out control signals to CPU, memory, and input-output device ports to ensure proper operation, okay? And the control signal could be memory read, READ, memory write. It could be read input port. It could be write output port. Could be interrupt. It could be interrupt acknowledged, bus request, bus grant, and so on. So these control signals indicate the type of action taking place on the system bus. So it should be noted that the system bus is a communication medium for data transfer, okay? And such data transfer is usually referred to as bus transaction, okay? So bus transaction could be memory read, memory write, input output read, and so on, okay? And the bus transaction usually involves master slave. So the master is the initiator of the transaction, while the slave is the target of the transaction. And then we have the CPU, the central processing unit, because we now have to deal with the devices. So for the CPU, we know it is the heart of the computing system, okay? The central processing unit. You know, so it acts as the controller of all the actions and services provided. So it executes the following cycle forever, okay? That's the CPU. It fetches, then decodes, and then executes. So these are the operations the CPU performs, you know, on and on and on. So it fetches an instruction from the memory, fetches instruction from the memory. Then it decodes the instruction, decodes the instruction. So in other words, it identifies the instruction, and then it executes the instruction. That is, it performs the action specified by the instruction. So this process is usually referred to as the execution cycle of the CPU. Execution cycle of the CPU, okay, which is the fetch, decode, execute, okay? So fetching an instruction from the memory involves placing the appropriate address on the address bus and then activating the memory read signal on the control bus to indicate the memory unit that the instruction should be read from that location. So the time required by the memory unit to read the instruction at the address bus is called the access time. Now, the decoding function involves identifying instruction that has been fetched from the memory. So it is the process of finding the type of instruction fetched, which is the decode cycle. And then the execute cycle executes the instruction. So the processor contains hardware consisting of control circuitry and an arithmetic and logic unit. So the control circuitry is needed to provide timing controls as well as to instruct the internal hardware components to perform a specific operation. While the ALU, which is the arithmetic logic unit, is responsible for performing the arithmetic operations, the logic operations, and the likes. And also we have the memory. So the computer memory consists of tiny electronic switches, okay, capable of switching between two possible states, either a 0 or a 1, okay? So memory, we see this more like a switch for switching between zeros and ones, or open and close. So switching represents binary digits. So memory is said to consist of large number of bits. And bits can be organized into groups of 8 bits, which we call bytes. It's usually 7 bits with 1 parity bit, so 8 bits, which is byte. And then the memory is said to consist of an ordered sequence of bytes. Like we know that the Pentium can address up to 4 gigabytes, which is 2 to the power of 32 bytes of main memory, okay? So that is the address bus of Pentium has 32 address lines. That's what it means. So the number is referred to as the memory address space, okay? That's memory address space, okay? So in other words, for the Pentium, it can support 32 bits. Processor here supports 32 bits addresses, okay? That's the implication. So here we have that the memory unit looks something like this. Yeah, this is to the data. Then here we have address bus. Then here we have read. And here we have write. So system memory consists, or better still, supports 2 basic operations, okay? The memory supports 2 basic operations, which are the read and write, okay? Read and write operations. So read reads a previously stored data, the read operation, while the write operation stores a value in memory. So the address and data of the memory are connected to the address bus and the data bus respectively. And then we can read and write signals, from, these control buses. So metrics used to characterize the memory are the access time and memory cycle time. Okay, so the access time, let's come this way. Access time is the amount of time required by the memory to retrieve the data at the address location, while the memory cycle time is the minimum time between successive memory operation. The minimum time between successive memory operations. Okay. So I think we can now probably summarize the typical read cycle and the typical write cycle for the memory. Okay. So steps in a typical read cycle in terms of the memory, right? More like an algorithm, right? So the first thing here is place the address, place, sorry. Location to be read on the address bus. Okay. And then the next point is to activate the memory read. Activate the memory read control signal on the control bus. And then you want to wait for the memory to retrieve the data from the addressed memory location, and then place it on the data bus. Then you want to read the data from the data bus, and then finally you drop the memory read control signal. To terminate the read cycle. That's a typical, read cycle algorithm. And then for the write cycle algorithm, we have steps in a typical write cycle. In the same way, one, we want to place the address of the location to be written on the address bus, and then place the data to be written on the data bus, and then you want to activate, just like in the case of the typical read cycle, you want to activate the memory write control, not read control this time, write control signal on the bus control. And then you want to wait for the memory to store the data at the addressed location. And then finally, just like we mentioned in the case of the typical read cycle, you want to drop the memory write signal to terminate the write cycle. Okay, and then you already know the types of system memory. Okay, so system memory may be implemented using a variety of memory chips, which comes in diverse speed, manufacturing technologies, and sizes. So who can help me out with the types of memory? Okay, been doing all the talking in the last 40-something minutes. Okay, types of memory. Who can help me out? Matthew, Emin, can you please help us out with some types of memory that you already know?
Is SRAM the type of memory?
Okay, okay, SRAM. Okay, so SRAM stands for static RAM, right?
Yeah, static random access.
Okay, can you give me the two broad categorization?
Of SRAM.
No, of system memory. The two broad categories.
I think it's volatile memory and non-volatile. The volatile are like the RAMs and SRAMs and DRAMs. Then the non-volatile is like the ROM, the read-only memory.
Okay, so I think I want to make a switch on that. Thank you very much, Matthew. Okay, now we have the read-only memory, and then we have the read-write memory. Okay. Now, these are the two broad categories, and we'll go into them briefly. I'll just mention a few things, and then that will be it. Okay. Now, when we talk about the properties of system memory, then we'll begin to talk about random access. Okay, let me change the color. Properties of system memory. Well, I don't want to wipe the board. I want to just wrap up this on this page. Now we have random access, right? Random access. System memories are random access memories. That is, accessing any memory location for reading or writing takes the same time, okay? That's the implication. So the random access here means accessing any memory location for reading or writing takes the same time. And then that's one property. Another property is volatility. Volatility, right? Hope I'm correct. Okay. Now, a volatile memory requires power to retain its content, right? Means it requires power to retain its content, right? That's why it's volatile. And then the third property of system memory is non-volatility. So a non-volatile memory can retain its value even in the absence of power, okay? So now, before now you were told read-only memory, random access memory. But, well, we want to say, well, these are the properties, okay? So let's see what type, relative to the types of memory, which of them possess some of these properties. So let us start with the read-only memory, okay? One, read-only memory. Then, now, they are mostly factory programmed and cannot be altered. Okay, it means they are non-volatile. Okay, so they possess this metric, Okay, they are non-volatile and cannot be written into. So the program that controls the standard input and output function, that is the BIOS, the basic input output system, is kept in the read-only memory of your computing device, okay? And now, some of the read-only memory types we have are the programmable read-only memory. So let's say this is ROM, all right? So we have the programmable read-only memory. And they are useful when the content of the ROM is not yet fixed. That is when the program is still in the developmental stage. So in programmable ROM, a fuse is associated with each bit cell. So to read a 1, the fuse has to be on. And to read a 0, the fuse has to be turned, is it turned off now or burned that's to burn, right? B-U-R-N, by sending high current. Okay, so once burned, the programmable or writing process is irreversible. That's for the programmable ROM. Then we have the erasable programmable ROM. Erasable PROM, EPROM, right? So they call this PROM, and they call this EPROM. So the EPROM offers further flexibility during prototyping, okay? So the contents of the EPROM can be erased by exposing it to ultraviolet light for a few minutes. So once erased, EPROM can be reprogrammed, unlike the programmable ROM. Then we also have another type of the read-only memory, which is the flash memory. Now, the flash memory is a special type of the electrical or electrically erasable PROM, okay? Now, let me talk about the electrical EPROM first, which is the EEPROM, right? It allows for further flexibility by allowing the user to selectively erase content. So there's no need for a special ultraviolet chamber to erase the entire content. That's just the difference between the EEPROM and the EPROM. While the flash memory is a type of EEPROM, but the basic difference is on how the content can be erased. So EEPROM is byte erasable, right? Erasable. While flash memory is block erasable. Block erasable. So writing in the flash memory involves erasing a block and rewriting it, okay? Not just some bytes. So you note that current systems use flash memory for BIOS so that changing BIOS version is fairly straightforward. You just flash the new version, like say you want to go and flash your phone, right? So you just flash the new version. Then they are also used in digital cameras, video game systems, and all of that. So these are the types of read-only memory. How about the read-write memory? So let us look at the read-write memory. Read, write, memory. So they're also known as random access memory, random access memory. I think you're used to this, which is RAM. Okay. And they are categorized into two major groups. We have the static and the dynamic. Okay. The static and the dynamic group. Okay. And now, for us to now go on this, for the static RAM, which you mentioned earlier, Mr. Emmanuel. The static RAM retains data once written, so long the source of power holds its value. So it is used for the implementation of processor registers and memory caches or cache memories. So we use this for processor registers and cache. Now for the dynamic RAM, which is the DRAM, this is SRAM. Then for the DRAM, dynamic RAM, it's actually a complex memory device that uses a tiny capacitor to store bits. Okay, so here we use capacitor in terms of design. So a charge capacitor represents 1 bit. Since capacitors slowly lose their charge due to leakage, they must be refreshed periodically to replace the charges representing 1 bit. So we now have other types of DRAM. We have the fast page mode, which is fast page mode, DRAM, or you say FPM DRAM. So they exploit the fact that we access memory sequentially most of the time. So that is, we look at how the memory is organized. So initially, memory is organized as a matrix of bits, like the 32 MB memory could be organized as 8K rows. Okay, so we have 8192, since K is the same as 1024, which is to the power of 10, you know. So to access a bit, we require the row address and the column address. So the fast page mode DRAM represents part of the memory with the same row address. So if you want to access a page, we specify the row address once. So we can read the bits in the specified page by changing the column address. So since row address is not changing, then we save on the memory cycle time. All jargons you know before now. Then we have the extended data output DRAM. This is extended data output. So it's another type of fast page mode DRAM, you know, that exploits the fact that we access memory sequentially, but it uses pipelining to speed up memory access. So it's let's say in this case, it initiates the next request before the previous memory access is completed. So these two types, the fast page mode and the extended data output, are asynchronous. Since their output is not synchronized to a clock, okay? Their output is not synchronized to a clock. Then we now have the synchronous DRAM. Which uses an external clock to synchronize the data output. So synchronization reduces delay and improves memory performance. So the SDRAM is also called single data rate SDRAM, as the supply data once per memory cycle. Then we also have double data rate SDRAM, which provides data at both rising and falling edges of the clock. And this effectively doubles the memory bandwidth and satisfies the high-speed transfer rate of faster processors. Then we also have the rambus DRAM. So it takes a completely different approach to increase the memory bandwidth. So this technology was developed and licensed by Rambus, and it's a memory subsystem that consists of RAM, the RAM controller, and a high-speed bus called the RAM bus channel, just like the DDRAM, the DDR, SDRAM, and RDRAM performs to transfer per cycle. Well, that's just a quick recap on what you already know. And then we have the input and the output devices. Okay. So here we have a single block diagram here. We have data, we have status, then we have command. Okay. Then, so this is more like the input-output controller. We have the input-output device. So we have address bus, data bus, and here we have the control bus. So all of this forms the system bus, right? So this is the input-output interface. So for the input-output devices, they provide the means by which a computer system can interact with the outside world. So input devices could be your keyboard, mouse, your output devices, your printers, and the likes. Then we have a peripheral devices, which are used to communicate with the outside world and also used to store data like your modems and the likes. Now, the input-output controller acts as an interface between the system and the input-output devices. So it provides the necessary low-level command and data for proper operation of diverse I/O devices, and it is used to regulate the amount of electrical power used to send signals on the system bus. So that, is just a quick recap on the computer organization.